Yeah.
All right, I think we're all set then. Looks
Yes.
like it. Great. Okay, well, good afternoon, everybody. I want to thank you for taking the time out of your day to join us in the HelioWAVE presentation. This is Group 7, along with me today, with what we have labeled as the world's most elite sun tracking heliostat. My name is Jacob Wissinger. With me are all mechanical engineering students here at UF. And to begin with, I'd like for each of us to go ahead and give a unique skill that we believe we've acquired over our time here and/or in industry. And for myself, that would have to be writing operating procedures and manufacturing control instructions.
Hi, my name is Elijah Crane, and I would say that my main skill I gained here was programming and software development, specifically with simulations.
Hello, I am Tyler Grenay, and I feel that my two main skills that I acquired while here at UF is CAD design and structural analysis.
Hello, my name is Courtney Gill, and I feel like I have helped a lot with the project management and organization within this group.
Hi, my name is April.
Hi, my name is Stephen Jenkins, and I feel like I specialized in mechanical analysis. Wow.
Hey everyone, my name is Lane Oots, and I'm really passionate about CNC manufacturing.
All right, now it's time for me to go. Hi, my name is April Seebach. I specialize in dynamics and controls and circuitry.
All right, awesome. So we'll go ahead and roll on here. So taking a first peek at our design here on the right side of your screen, you can see a model human figure next to the HelioWAVE design, which has been slightly modified since this image was taken with the addition of a few additional components. The figure there is about 5'9", and the heliostat adjacent to him is about 1 meter squared of reflective surface. The deliverables for this project were to design a small scale heliostat, which would be capable of being mass produced and put into the Las Vegas, Nevada desert, with the desire to reflect sunlight to a central aperture with maximum concentrated solar energy. And some of the challenges and goals of this project were to overcome the ambient conditions present in the Las Vegas desert. In addition to that, we wanted to achieve dual axis tracking with our reflective surfaces. And with these reflective surfaces, we desired to cause the greatest accuracy and efficiency possible with our design. So taking a peek at the motivations behind our design choices, we can really break these up into 3 main categories that we set for ourselves to find our basically overarching goal for our project. Those 3 categories were what do we believe we're best at, what we are passionate about, and then what drives our economic engine. And summarizing and extrapolating from this over the course of an hour's worth of brainstorming, we were able to conclude that number 1, design for manufacturability, and number 2, optimization would summarize these personal traits that we have gathered during our time here at UF. And that became our primary motivation. And I know, so this next slide is a lot to look at. It is our customer needs flowchart, so bear with me. On the left-hand side, you can see all the needs that we summarized from the customer needs statements. Adjacent to that directly, you can see the metrics assigned to each of the summarized needs. Following there, you can see the 4 subsystems that we selected to put into our design as a primary overarching full system. And then to the right of that, you can see the functions that each of these subsystems would provide for our design.
So now I kind of want to go over, this is on this slide, we're going to find a basic, this is our heliostat module, and I want to highlight some things for everyone. As you saw on the previous slide, we broke up our heliostat into 4 different modules, that being reflective surface, structure and mounting, actuation, and control. So just highlighting some of the bullet points on this slide, some of the key features that we identified with our design. The reflective surface is capable of 1.2025 megawatts of concentrated thermal input. And with our safety mode, which will be described later in the presentation, we have a factor of safety of 39. Moving to structure and mounting, we kind of have our chassis sitting on top of 2 structural support legs, and those support legs have a bending factor of safety and buckling factor of safety of 10 and 10.8 respectively. Actuation, you can kind of see the arrow pointing to one of our motors. With that, we have a 56.7-year design life, and this motor is capable of 360 degrees range of motions of our chassis. And then finally, the little black box in the bottom, that's our control subsystem, which features -91 decibel milliwatts and 11 megabits per second Wi-Fi module. And that allows us to achieve a half degree of tracking accuracy. So this is kind of a visual overview of all of our different subsystems. As I previously stated, we have reflective surface, and you can see kind of sort of broken down a singular module picture beneath that. Likewise, we have structure and mounting with another picture showing that. We have our control system and actuation kind of showing an exploded view of what really makes this thing move. So first thing we want to talk about, the first module is our reflective surface module. Couple things I want to point out here. Our reflective surfaces are housed in this chassis. So we have a kind of a unique shaft mount. Each reflective surface sits in a 1-inch diameter circular shaft with a flat milled out of it, with little overhangs and set screws to prevent motion of the mirrors while the heliostat is being operated. Kind of towards the bottom of this picture, we have like a box that houses our motors that actuate the mirrors in the azimuth direction. And then the last arrow just highlights the chassis. So that's a brief overview of our reflective surface module. And next, we're going to go into some more analyses.
Right. So here we're going to highlight a few of the key features of our reflective surface that differentiate it from other designs. First is its high concentration ratio, which is provided by the silver-backed silica glass reflective surfaces. These supply high reflectivity, which overall increases the concentration ratio and thus the concentrated focal thermal input. We also have an incredibly low surface to module ratio, which prevents the heliostats from shading each other as they rotate about the azimuth, which also prevents any kind of optical losses due to shading, which again increases the concentrated focal thermal input. Another key feature of our reflective surface is its wind resistance. So as Lane mentioned in the previous slide, we have a safety mode when wind gusts reach anywhere above 50 miles per hour, where the entire module rotates to where it's completely flat. This allows the force of lift and drag on the module to be drastically reduced in these high wind speeds, which prevents the module from being basically ripped out of the ground when the winds get really high. Next slide. And you can see this in this slide right here, where we do a quick wind analysis to kind of show the factor of safety against wind resistance for this module. So as you can see, the force of lift in that first equation right there equal to 1/2 coefficient of lift times rho times area of the module times velocity squared. We approximated this module as a NACA 9412 airfoil. As you know, airfoils with a non-zero camber have a non-zero lift coefficient at zero angle of attack. So we kind of considered this as a worst case scenario, being that our coefficient of lift was found to be 0.8. And as you can see, we plugged in some other parameters there. And we got a total upward lift force on the module when it is flat of 296.2 newtons. The required shearing force to basically cause the bolts that attach the module to the lower leg supports to fail was found to be 11,560 newtons, which, as you can see, this corresponds to a factor of safety of 39, which is more than adequate to prevent this module from failing in the event of high wind speeds. Additionally, our module meets the customer requirements for concentrated focal thermal input. So if you do a heat transfer analysis on the receiver tower, you have the energy coming into that receiver as the energy that is reflected off of all of the modules in the entire field. That's just equal to the number of modules in the field, which we assume to be 1,500 in this situation, times the energy reflected per module, which is a function of both the radiative energy from the sun shining down onto the module, the total area of the reflective surface, the angle of reflection of the reflective surface, and the optical efficiency of the reflective surface. And then the heat lost from the receiver is just the radiative heat that comes from the temperature of the receiver itself, which was assumed to be 1,000 degrees Celsius. So plugging all of this in to this equation, you get a concentrated focal thermal input of 1.025 megawatts, which is more than adequate to meet the customer requirements for concentration ratio and concentrated focal thermal input.
All right, so now looking at the structure and mounting subsystem, we have just a CAD rendering of our overall structure. So here you can see our chassis. It is made of AISI 1020 steel U-channel with a 1-inch outer profile and then a 1/8 thickness for the walls of that. And so that composes the chassis, and the shafts inside that hold the reflecting surfaces are mounted via pillow blocks that you can see at the top and bottom of the chassis. And then the main shaft as well is connected to the chassis via these pillow blocks. And both of these shafts are 1-inch 1020 steel rods. And then these are mounted into concrete footings that are sunk into the ground to reduce tipping and uprooting during any wind forces. Okay, and then getting into the structure and mounting key features. So one of the main things we made sure to do is to balance the chassis, as the frame, the shafts, the motors, the motor mounts, and the mirrors, they're all sitting on this main shaft. And since our reflecting surfaces are actuated through this main shaft, the motor is required to drive it. And so by balancing it, we reduce any moment caused by the chassis to reduce cost and reduce the power requirements of this motor. The next thing we made sure to do was use U-channel, because we wanted to use steel for its high stiffness to maintain that high tracking accuracy, but wanted to reduce the cost and the weight of this whole module. So by using U-channel, we were able to minimize the mass and the cost while keeping the accuracy. And then the next feature is the open frame design. So one of the big concerns obviously was wind. So by having this open frame, we reduce any impacts of wind on a wall or anything. And so this just improves the aerodynamics, and it also allows for water to flow cleanly off the reflecting surfaces, as the reflecting surfaces will need to be cleaned due to accumulation of dust and whatnot. Pillow blocks were used for this design because they very tightly restrain the shafts from translating in any direction, but they allow very free rotation as they have a low coefficient of friction due to the embedded bearings in these pillow blocks. And then the final key feature is our mirror clamping shafts. So the shaft for the reflecting surfaces, it has two functions. Obviously, it supports the mirrors, but it also has that cutout mentioned earlier to allow for a soft tip set screw to be used to clamp the mirror into place to prevent it from sliding off.
Yeah, so to continue off of what Elijah was describing, our structure and mounting subsystem is going to conclude two main components that's going to ultimately be taking on the weight of the reflective surface module. The first component, as demonstrated in the slide here, is going to be the two shaft types, which will create the azimuth rotation and the elevation angle of the structure. As you can see, it was determined through bending moment calculations that the main shaft connecting the two support legs is going to present a factor of safety of 173. To go along with this, it was also found through calculations that the azimuth rotating shafts will present a factor of safety of 10. So ultimately, overall, the structure will not fail due to bending from the weight of the chassis. And then to go along with this, the second main component analyzed for our structure is going to be the two support legs, which are connected to the concrete blocks. For this component, we analyzed the buckling acting on the support legs, and it was found that a factor of safety of 10.8 is present. So overall, this proves that the chassis and acting on the support legs will not fail due to buckling, and ultimately the whole structure will not fail due to bending as well. And then to go with that, our structure mounting will be supporting 4 individually rotating shafts, which ultimately present 4 individual heliostats. The entire structure subsystem is going to be made of steel U channels, which fail at a melting point of 2,500 degrees Fahrenheit, which greatly exceeds the greatest ever recorded temperature in Las Vegas of 128.7 degrees Fahrenheit.
Now a bit into our control subsystem. Some key features of our control subsystem are its simplicity and accuracy. So there is only one Arduino Mega that is needed to control all of the components in this module, including the 3 motor drivers, the 5 encoders, and the ESP2866 Wi-Fi module. Additionally, all of these components can fit into a neat little compact, easy to manufacture 5.5 by 8 by 1.1 inch sheet metal box. In addition to its simplicity, it's also highly accurate. It implements closed loop angular feedback through the use of 5 positional encoders that are attached to each motor. This provides a robustness to any kind of uncertainty due to installation error or any kind of bending or deflection that could present any kind of tracking inaccuracy. The positional encoders will correct for that. And ultimately, a higher tracking accuracy leads to a higher concentrated focal thermal input, increasing our total amount of energy. Additionally, the ESP8266 Wi-Fi module contained within this control subsystem has an incredibly high transceiver sensitivity, which means that modules, even at the very edge of the field, will still be able to receive control signals from the main command tower, which will ensure that even modules at the edge of the field will still maintain that less than ½ a degree tracking accuracy, which again also far exceeds the customer requirements. So just some quick analyses to prove why we chose the components we did. So one of the customer needs, as you know, is that all heliostats in this module need to be controlled via Wi-Fi from a computer located in the central tower. That being as it may, we needed to choose a Wi-Fi module with the correct required bandwidth and transceiver sensitivity to accomplish this task. So when calculating the required bandwidth, we considered how many bits are needed to represent 360 degrees of motion to about ½ a degree of accuracy in binary, which comes to be around 10 bits per degree. We also considered the rate at which the sun moves across the sky, which is around 15 degrees per hour or 0.005 degrees per second. And we multiplied it by the number of heliostats per module and the number of modules per field to get a required bandwidth of a very small 300 bits per second to control the entire field of heliostats. We also, in addition to bandwidth, have to consider the sensitivity of the receiver module on the Wi-Fi module, because if these things are going to be communicating with and receiving signals from a central tower, we want to make sure that they are able to receive that signal. So if you consider the signal coming from the control tower to have around an average signal strength of around -60 decibel milliwatts. And if you consider how the energy radiates or the signal strength radiates out from the control tower, if it radiates out in kind of a spherical direction with a radius of 100 meters squared, and if you have a antenna area of around 25 millimeters squared. The required receiver sensitivity is negative 53.97 decibel milliwatts, which if you look at our ESP8266 Wi-Fi module on the right over here, it has a bandwidth of 11 megabits per second and a receiver sensitivity of 91 decibel milliwatts. So as you can see, this small, cheap, simple module more than adequately meets the customer specifications of Wi-Fi controlled heliostats. Another thing that I'm sure you're wondering is, why did we choose an Arduino Mega? Why didn't we go with a smaller microcontroller? Well, we did an analysis of the required number of digital input pins, digital output pins, and pulse width modulation pins required to control all of the encoders in the module, the motor driver, and the Wi-Fi module. So the number of input pins for both the encoders is around 2 per encoder for both channels of the encoder. And additionally, for the motor drivers, you need 4 digital output pins and 2 pulse width modulation pins per driver to control the speed of the motor. So all in all, if you add all of these up, that gives a required 24 digital INO pins and 7 pulse width modulation pins per module. So if you move on to the next slide, you can see here that the Arduino Mega is the basically the smallest microcontroller that we could find for the lowest price that meets these specs, with 39 digital INO pins, 15 pulse width modulation pins, and a 5-volt DC operating voltage. So that's why we chose this microcontroller.
Okay. Moving on to actuation. This image here shows the actuation components required to rotate the mechanism, and it shows the supports, the rotation shafts, and as well as the motors and the motor covers. And some key features of this actuation design is that we have a singular azimuth rotation axis, which allows us to have a lower motor to mirror ratio, whereas the conventional heliostat has 2 motors per reflective surface. Our actuation design allows us to have 1.25 motors per reflective surface. Another feature for this actuation design is the Denso gear motor used to power the azimuth rotation shaft, which is using gears to increase the torque so that we can get away with using a cheaper motor. And to move on to the analysis, in order to calculate or achieve the required range of motion for our heliostat, we needed to calculate the height of the chassis so that the sun rays would not get blocked by the chassis while it was going to the reflective surface. And after performing the calculations for that, we came at a chassis height of 0.123 meters. Additionally, we performed a design life motor analysis on the motors, and to do that, we took the distance traveled in 10 years, the total distance of the motor, as well as the distance traveled per day, and then we divided the distance traveled per day by the total distance, which gave us the 56.7 years for our motor life.
And of course, with all things comes a cost, and we had some off-the-shelf parts that we couldn't personally make on our own, and those would be the motors, the pillow blocks, the fasteners, the gears, and the control box components like the Arduino Mega. And then a lot of the parts that we could manufacture ourselves, we decided to do that. And so those would be the raw materials like the steel, aluminum, reflective glass, and concrete, and those make up the chassis and the shafts. So the parts that we manufactured, the raw materials, are included in the manufacturing labor. So we found the manufacturing and assembly labor by determining the mean hourly wage of a production worker in Las Vegas, Nevada, and then we multiplied it by how long we thought the parts would need to be completed or assembled. So the manufacturing labor included the bandsaw cuts, the drilled holes for the fasteners, and the welding, which we replaced some of the fasteners that we needed and put welding to reduce the cost. And also the assembly labor includes the concrete setting that we had, the wiring of the control box, and putting the fasteners into the chassis. And then the energy consumption is any of the cost of any manufacturing process that requires energy. So the welding, the cutting, the drilling, all of that uses energy, and that cost was included in the assumption. And the total cost, therefore, would then be around $189. So in summary, our design is unique because the U-channel chassis provides aerodynamic frame to support reflective surface. It has a dual independent axis tracking system for each reflective surface, and that increases the tracking accuracy. And then the reflective surface has a compact configuration to minimize the heliostat design. And in conclusion, even though we have a high cost, we have other unique features like the tracking accuracy and structural robustness, which ensure that other customer constraints are received. And our goal within the project to have optimization and simpler shape to have easier manufacturing was also achieved within the project. Thank you so much for your time.
All right. Do we have questions from our panelists?
So yeah, this is Rick Miles with Northrop Grumman. I'll go ahead and start off. There was something early on. Well, first off, good presentation. But if you could go kind of towards the beginning where you actually you did a thermal analysis. And while you're getting there, just a general comment. You show pictures of your heliostats, and the mirrored surface does not look mirrored. I would have made it something that is more consistent with to get across the fact that it's mirrored when you're presenting to your customer, right? It looks dull and doesn't get across the fact that it's a reflecting surface.
Professor Trong, can you enable screen share again?
Yeah, sorry.
Thank you.
There you go. Yep.
Was this a slide?
Maybe back one slide. Oh, maybe it is with the. So there was a comment where someone mentioned that it was. I was looking for it. Yeah, right there. Okay, right. So your outgoing temperature, you're assuming 1,000 degrees Celsius. That seems awfully high.
Yes, that was actually provided in the customer needs statement. They said assume a receiver temperature of 1,000 degrees Celsius. So that's why we have that.
Okay, that's just, I mean, that's above the melting point of aluminum. That's why I was curious. Okay, and then so you're going to do 1,500 of these modules, which would be 6,000 heliostats. Do you have a general idea of how that's going to be arrayed out in the field? Is it just like a linear stagger pattern, or how is it in relationship to what the receiver versus the transmitter? Maybe I just missed that in the presentation.
Yeah, we most likely it would be in, as you suggested, a linear stagger pattern to prevent any kind of shading of the modules. I know there's some research papers I found with specific formulas of how, based on the size of the module, how you would arrange these heliostats in the field, but that's something that we will most likely further consider as we move further along in the design process.
Okay. And then there was a, okay, thank you for that clarification, Dr. Trump. So then you chose to go with 4 motors, so 1 motor for each heliostat. I'm curious if you looked at going with 1 or 2 motors with some sort of drive belt type mechanism, because I assume that your motors were a fairly large part of your cost.
Yeah, that was another that was another feature of our design we definitely considered. We did consider trying to use fewer motors, but we found that having actually individually independently controlling each heliostat via the use of the positional encoders increased the tracking accuracy by a lot. So hence that's why we made the decision to sacrifice cost for a higher number of motors.
Okay, and then if you could go to your cost slide. So that pie chart in the upper right doesn't make sense compared to your table down below. I don't know if you're rolling some of the materials costs into your labor as well. Or if you're just trying to show labor and energy consumption, it's very confusing compared to the table that you provide. In my opinion.
There was an accident that we didn't see at the very beginning, that the pie chart, we changed the costs later. And so the pie chart is different on accident. We apologize for the error.
Oh, no, that's okay. Just something that caught my eye. And then finally on cost, I would add, so based on when I look at customer needs and when you talk to customers, cost is usually a huge driver, right? And so your price point that you're attempting to get to is $100. You're almost double that. And I understand your discussion of why you would, but that's usually a very tough sell to the customer. So do you have any plans to modify your design to try and drive that cost down?
Yeah.
Yes. Sorry, Elijah. Yes, we do have various plans to reduce the cost. We actually started out with the poster presentation at 400 something. So we've been like figuring out multiple different ways to decrease the cost, many of which I tried to mention. So like welding instead of the use of so many fasteners. And we're changing the motor covers and the motor mounts to be a different material than steel, since those don't actually need any structural, like those don't have structural function. So we're changing those to like be 3D printed instead of steel. So we are trying to find many ways to reduce the cost to try to get it back down to more in the range of the customer.
Okay. And I've got a couple of more questions, but I'll let other people ask, and then if there's time, we'll get back to mine. Thanks.
Okay. Other questions from our panelists?
Okay, I guess I'll continue on. Did you go to where you do your buckling analysis? All right, so there you're assuming a fixed free condition. Is that basically fixed in the ground and free at the top? Is
Yeah.
that kind of...
So it was using the Euler's column buckling analysis, and yeah, fixed free. So like that's where the 0.25 comes from in that for n in that equation.
Okay, and then and I just might have missed it. How is it? What load are you assuming here when you have that 400, where's that 400 coming from?
Yeah, so that's the mass of the chassis. So just like basically the load on the legs from from supporting the chassis and the shafts and everything. So it was basically just analysis of how close is this thing to failing, just if you just set it up and put it on the ground.
Okay, so right, so you're going to have wind loads that you're going to have to deal with as well, right? For potentially from a buckling situation. So you're going to have to look at potentially, you're going to drive down. You're probably still good with your factor of safety there. It's just going to drive it down a little bit to also consider that as well.
Yeah, yes, sir. Yeah, that is something we need to look at for sure.
Okay. And then could you go back one slide? I think slide 13. Same thing here with your bending analysis. What is your assumption on your load here? You're just assuming a distributed load across the heliostat. What's the loading that you're assuming?
Yeah, so for the main shaft, it was actually modeled as, like the main shaft being the one connected to the legs, that one was modeled as fixed with 2-point loads, where the pillow shafts from the chassis would interact with the shaft basically. And then for the reflecting surface shafts, that was just modeled as a distributed load basically from the mirrors on it. With that and fixed for the pillow blocks.
Okay. So I just a suggestion. I would suggest maybe doing a shear and moment diagram here with a free body also associated with it to make clear how you're loading up this structure, because I'm not quite certain that the assumptions that you're making there are correct, but I would have to kind of see what you're looking at from a free body diagram standpoint.
Yeah. We did do more in-depth analysis for one of the previous projects, but it was kind of difficult to make those fit in here. So that's why we went with a more simplified just demonstration of its safety. But yeah.
Okay, fair enough. And a general thing, there was something where you gave the dimensions, I think, of the Arduino box. Yeah, so here I have no idea what the 5.5 by 8 by 1.1 is, right? There's no units there. So just make sure that you're consistent, right? Because sometimes people will look at these presentations without getting the presentation from you. And so you want to make sure that they're always making the proper assumptions. The other thing is throughout your presentation, you seem to shift with your temperatures between Celsius, Kelvin, and Fahrenheit. Try and be more consistent with the way you present your temperature data so that one slide can relate to the other very easily, and the person who's viewing the presentation or looking through the presentation can relate one thing to the other.
Yeah, thank you. We appreciate it.
Yeah, thank you.
And that's all I've got.
I jump in?
Yeah, I was hoping you would jump in because of all the neat control and computer speed calculations that these guys did.
Yeah, I admit, first when I was reading over your slide, I was like very confused on why you needed a Omega and why you were calculating in all of the modules. And now I understand that you have like 5 different axes that you're driving.
Mm-hmm.
So with those 4 or 5 different motors, what do you have in terms of limit switches for calibration and end stop?
All right. I think, yeah, that's a Jacob question, because you've been working on adding those limit switches to the design.
Yes. So since we do have the 5 motors in this design, we have the 1 for alpha rotation and the 4 for the azimuth, being the reflective surfaces themselves. So post creation of this presentation, we have added an alpha limit switch to that. And we plan to add azimuth limit switches as well. In April, I believe that would take 5 more pins off of our Mega, correct?
Yeah, but again, our Mega has 39 digital INO pins. We're only using 24 of them. So we got plenty of pins left to add in those limit switches.
Okay, are you gonna do 1 per axis or 2 per axis?
I believe we were, so this is a like a homing switch, correct? So we believe the best method for perhaps the startup of this module would be to rotate downward. And in the new design, or at least in the addition to the design, the limit switch would contact one of the legs and let it know where it's at, so we can begin the day at the required angle. And as far as the azimuth direction, it would also be a command where all those motors rotate counterclockwise.
So you're just using them for initial calibration and not for end stop.
I'm sorry, actually, I had something take over my Bluetooth and I missed a lot of what you said. Could you please repeat that?
So you're using them just for calibration and not for end stop.
Correct.
Do you have any hard stop?
That is something that we have yet to look at, but I believe that's very important and we will do so.
Okay.
I may have missed it, but did you have a thermal expansion analysis for the kind of the longer rods that are underneath the glass?
So we did an analysis of the thermal expansion of the glass inside the shafts because there was concern about if they expanded too much, would they basically shatter themselves when they were in restrained thermal expansion. But we did not do any analysis for the shafts actually, but that is a good point.
Yeah, the interplay between the two might, and how much they expand versus the glass.
Mm-hmm.
Okay. Do we have any additional questions from our panelists? Okay. Then this is probably a good time to wrap up because we're right at 2:45. So I want to thank this group for a semester of hard work and a really great presentation. A lot of really unique analyses that we've only seen from you guys. So appreciate kind of the creativity that you guys put into coming up with some of these analyses and carrying them through and kind of interpreting the results for us in a way that made sense. So really appreciate that. I think you guys did an excellent job and looking forward to having most of you in 4502, and we'll see if this one maybe is one that we can actually prototype. I think with that, we'll wrap up. The next session is 4 o'clock today for the panelists at Northrop and the other sponsor companies. So we'll check back in with you guys at 4. With that, let me stop recording.